Welcome to the General Chemistry 1 class. This section is on mass relationships in chemical reactions, focusing on limiting and excess reagents. In this lesson, we will explain the concept of limiting reagent in a chemical reaction, identify the excess reagent. In real practice, reactions are performed in which a reactant or reactants are used in excess with another reactant. It means that the ratio of reactants is not proportional with the ratio of substance in the corresponding balanced chemical equation. It is usually intended to cause a reactant to be used up in the given reaction. In such cases, the reactant which is allowed to be used up in the reaction is called a limiting reagent. So called because it limits the maximum amount of the product that can be formed. And on the other hand, a reactant used in excess in a given reaction is called the excess reagent. To illustrate it, the concept of limiting and excess reagent, consider 4 burgers and 7 bottles of soft drinks, and you are asked to prepare meals consisting of 1 burger and a bottle of drink per meal. Given the number of burgers and bottled drinks, you can prepare 4 meals, while 3 bottles of drink remain unpaired with burgers. Comparing the example of a chemical reaction, let the burgers and bottled drink be the reactant and the meals be the product. As we can see in the illustration, it is the burger that limits the number of meals prepared, the product. And the burger is then the limiting reagent for the reaction. On the other hand, the bottled drinks come in excess, and some of them have no more burgers to be paired to them. In this case, the bottled drinks can be compared as the excess reagent for the given reaction. To identify the limiting and excess reagent for a given reaction, stoichiometric calculations are necessary. Consider a reaction considering of A and B as reactants and P as the product. The masses of the reactants must be converted first to number of moles using their respective molar masses. From here, the number of moles of the reactants are converted to the number of moles of the product using the mole ratio based on the balanced chemical equation. If the reaction has 2 or more products, consider the product of interest. Usually, it is one of the given emphasis in the problem. The reactant that gives the smaller amount of the product is the limiting reagent, while the reactant that gives the greater amount of the product is the excess reagent. Determining the limiting and excess reagents are necessary to quantify the expected amount of product that can be formed. To give the mass of the product formed, given the amounts of reactants, consider the number of moles of the product from the limiting reagents is converted to mass using its molar mass. Sometimes, the number or the amount of excess reagent remaining after a reactant is quantified. To do this, first, convert the number of moles of the limiting reagent to the number of moles of the excess reagent. Using the mole ratio based on the balanced equation, this will give you the number of moles of the excess reagent being consumed. Second, subtract this value from the initial number of moles of the excess reagent, which is the amount of mixed with the limiting reagent. At this stage, you will obtain the number of moles of excess reagent remaining. And third, multiply the number of moles by the molar mass of the excess reagent to determine the mass of reagent that remains unreacted. Let us apply these rules in some examples. Let's have aluminum oxide was prepared by combustion of aluminum metal according to the equation. 4 moles of aluminum combined with 3 moles of oxygen producing or yielding 2 moles of aluminum oxide. In a closed chamber, a 0.5024 mole sample of aluminum metal was combusted in the presence of 0.4573 moles of oxygen. Which of the two reactants is the limiting and the excess reagent? And second, how much aluminum oxide are generated in the reaction? And lastly, how much of excess reagent remained unreacted? To answer the first question, let us first compute the mass of aluminum oxide that can be produced from the given amount of reactants. Let us start from calculating the number of moles of aluminum oxide if aluminum would be used up in the reaction. The mass of aluminum oxide equals 0.5024 moles of aluminum times the mole ratio, which is 2 moles of aluminum oxide per 4 moles of aluminum. Simplifying, we get 0.2512 moles of aluminum oxide. Now, for the moles of aluminum oxide from the moles of oxygen, the number of moles of aluminum oxide equals 0.4573 moles of oxygen times the mole ratio. 2 moles of the aluminum oxide per 3 moles of oxygen. Simplifying, we get 0.3049 moles of aluminum oxide. At this point, we can now compare the amount of the product that can be formed given the amounts of reactants. Remember that the reactant gives the smaller amounts of the product is the limiting reactant, and looking at the values, aluminum gives smaller amount of product. Therefore, the limiting reagent is aluminum, and the excess reagent is the oxygen. To solve the expected mass of the product, let us consider the number of moles of aluminum oxide from the limiting reagent. By multiplying this to the molar mass of aluminum oxide, the mass in grams of aluminum oxide is obtained. Plugging all the given values, mass of aluminum oxide equals 0.2512 moles of aluminum oxide times 101.96 grams per 1 mole, which is equal to 25.61 grams of aluminum oxide. To calculate the mass of grams of the excess reagent that remain unreacted, let us determine first the moles of the excess reagent of oxygen that has reacted with the limiting reagent aluminum. The moles of the oxygen that reacted equals 0.5024 moles of aluminum times the mole ratio, 3 moles of oxygen per 4 moles of aluminum, giving a value of 0.3768 moles of oxygen. This is the amount of oxygen that has been used up by aluminum. The next step is to calculate how many moles of oxygen remain unreactive. Out of 0.4573 moles of oxygen initially present, 0.3768 moles is consumed. By getting the difference, we get 0.0805 moles of oxygen. This is the number of moles of oxygen remaining. The last step to be done is to convert the number of moles of unreacted oxygen to mass. To do this, just multiply the moles of unreactive oxygen by the molar mass of oxygen. Plugging in the values, mass of oxygen, unreacted equals 0.0805 moles of oxygen times 32 grams per mole. Simplifying, we obtain 2.58 grams of oxygen. Let's have example number 2. Urea, a compound used as fertilizer, is industrially prepared from ammonia and carbon dioxide according to the equation 2 moles of ammonia plus 1 mole of carbon dioxide producing 1 mole of urea and 1 mole of water. A reaction vessel was loaded with 428.7 grams of ammonia and 850.0 grams of carbon dioxide. Question number 1. Which of the two reactants is the limiting and the excess reagent? Question number 2. How many grams of urea can be generated in the reaction? And question number 3. How many grams of the excess reagent remained unreactive? In answering the first question, let us start from converting the given masses of reactants to the number of moles. To do this, just divide each mass to the corresponding molar mass. For ammonia, number of moles equals 428.7 grams divided by 17.034 grams per mole, which simplifies to 25.17 mole of ammonia. For carbon dioxide, its amount in moles equals 850.0 grams divided by 44.1 grams per mole. So this value, or this gives a value of 19.32 mole of carbon dioxide. From the number of moles, calculate the number of moles of urea that can be produced if the reactants would be used up in the reaction. From the moles of ammonia, the number of moles of urea can be calculated by multiplying 25.17 moles of ammonia by the mole ratio, which is 1 mole urea per 2 moles of ammonia, given a value of 12.59 moles of urea. If carbon dioxide would be used up in the given reaction, the number of moles of urea equals 19.31 moles of ammonia times ratio of 1 mole of urea per 1 mole of carbon dioxide. Simplifying gives us 19.31 moles of urea. By comparison, we see the ammonia gives the smaller amount of urea in the reaction. This means ammonia is the limiting reagent while carbon dioxide is the excess reagent. To determine the mass in grams of urea that can be generated in the reaction, let us consider the number of moles of urea that can be formed from the limiting reagent. The value is then multiplied by the molar mass of urea to give the answer. Plugging in the values, mass of urea equals 12.59 moles of urea times 60.062 grams per mole. Simplifying this equation gives us a value of 756.2 grams of urea. To determine the mass in grams of excess reagent that remain unreactive, we first need to calculate the number of moles of carbon dioxide that reacted with the limiting reagent ammonia. Moles of reacted carbon dioxide equal 25.17 moles of ammonia times the mole ratio 1 mole of carbon dioxide per 2 moles of ammonia. Simplifying gives the answer of 12.59 moles of carbon dioxide. The next step is to calculate the number of moles of carbon dioxide and reactant. Given that we initially have 19.31 moles of carbon dioxide used in carrying out the reaction, let us take away the 12.59 moles that has been used up. The difference is 6.72 moles is the amount of carbon dioxide that remain unreacted. To convert the number of moles of unreactive carbon dioxide to mass in grams, simply multiply the number of moles of unreacted carbon dioxide by the molar mass, substituting the values, and the mass of carbon dioxide unreacted equals 6.72 moles of carbon dioxide times 44.01 grams per mole, leading us to the answer of 296 grams. To summarize, the limiting reagent is the reactant which dictates the maximum amount of product that can be formed in a reaction. The excess reagent is the reactant that is present in excess of the exact amount needed by the other reactant to fully consumed. We have here our references or bibliography. Thank you and God bless.